A pen is drawing a line on paper, and it has been drawing it all night. A dry scratch, back and forth, hour after hour. 29 meters, a day unrolling under your hands. Then, in the summer of 1967, the same smudge keeps coming back. About 5 millimeters of ink in half a kilometer of paper. Your eye crosses it 100 times before it stops. So what is sending it? Jocelyn Bell had helped lay the 190 kilometers of cable feeding the paper. It gets caught only by someone reading like they expect to lose their job. Stand at that desk. The lamp makes a pool of light, the room beyond it cold and dark, and the eye is already past the mark when something stops and says, "You have seen this before." And in the margin, right beside that mark, somebody has written the coordinate by hand, 1919. And next to it, in pencil, a question mark. That question mark is the first human response to whatever this is. It took nearly 4 months just to prove that mark was real. Working out what it was took another year, and the answer kept changing on the way. The first wrong answer came from Anthony Hewish, the man who had designed the telescope. To see why he was so sure, you have to know what the sky looked like on paper at Lord's Bridge in 1967. Badly suppressed car ignitions, a sparking thermostat, an arc welder somewhere nearby. All of it lands on your paper as ink. The array had been built to catch quasars, the bright hearts of distant galaxies, twinkling in the solar wind. It caught every other kind of noise, too. Most of a radio astronomer's day went on deciding what to throw away. So when a graduate student says there is something odd in the record, the reasonable answer is the one you would give. There's always something odd in the record. She kept the mark anyway. She did not argue that it was real. She went back and pulled the older rolls. Weeks of them, from that same patch of sky, unrolled end to end in the attic of the old Cavendish laboratory. She crawled along them on her hands and knees to check the ink. The mark is there. Then there again. Same patch of sky. And it was arriving 4 minutes earlier every day. A month of that puts it 2 hours adrift of your clock. That is a signature. A welder keeps human hours. A car passes when a car passes. Anything you make on Earth runs on Earth's clock, and Earth's clock is the sun. The stars keep a different one. They come back 4 minutes earlier each day. In those 4 minutes, the Earth has slid along its orbit and has to turn a little less far to face them again. So the mark on the paper was not keeping our time. It was keeping the sky's time. Whatever was making it was not in the room, not on the road, and not on this planet. Once it was off the Earth, the next question was how fast it was doing whatever it was doing. The slow recorder could not tell. It smeared the mark into a blur. There was a faster recorder. From late October, she went out to the observatory every day to catch the source as it crossed, with the paper running fast enough to separate the pulses. For weeks, the fast paper came back flat. The source had gone quiet. Then, on the 28th of November, the pen moved. Sharp peaks, evenly spaced, 1 1/3 seconds apart, over and over, with the kind of regularity you would expect from a machine. She pulled the paper off the drum and measured the gaps with her fingers. Then she phoned Hewish. His answer was immediate. "That settles it," he said. "It is man-made interference." Nothing in the sky was supposed to keep time on that scale. A pulse that sharp, that even looked like engineering, because on a scale of seconds, everything that regular was engineering. She could not marshal the arguments fast enough. But she had the 4 minutes. The telescope was pointed at that patch again, and the source performed. That is where it stops being interference, and starts being something nobody wanted to say out loud. In the file, the source got a name credited to Hewish, to her, or to the group. LGM1, Little Green Men. The popular version of this story and the record disagree here, and they disagree about one thing: how seriously anybody actually took it. Some accounts call the name a joke, a placeholder nobody believed for a moment. Senior staff met privately, and the question they put to each other was how one announces the detection of life elsewhere responsibly, and who one tells first. Both of those are in the sources, and they are less contradictory than they look. A person can believe an idea is almost certainly wrong, and still be careful about the day it turns out right. They did not settle it by argument. They set out to kill the finding, 3 separate ways, each test designed to prove the mark was not real. Test 1. Maybe the pulses were a fault in the new array itself, a loop in its own wiring. So Paul Scott and Robin Collins pointed a completely separate telescope, with its own receiver, at the same coordinates. They saw the same pulses, not the instrument, then. Test 2 asked whether it was close by, a satellite, a probe, something inside the solar system pretending to be a star. Radio waves crossing interstellar space do not all arrive together. The space between stars is thinly salted with free electrons, and they drag on the low notes more than the high ones. So a single pulse arrives as a sweep, high notes first, low notes trailing. Measure the delay across the band, and the sweep tells you how much space that pulse crossed. John Pilkington did that measuring. By that measurement, roughly 200 light years. Far outside the solar system, and comfortably inside your own galaxy, which quietly settles something else. A signal that faint, arriving from that far away, has to leave its source enormously bright. Whatever is doing this is no transmitter anybody on Earth could build. Outside this building, nobody knows any of it. That was deliberate, and it is the part people later turned into an accusation. Ryle and Hewish had ruled that the data stay inside the Cavendish until every local explanation was gone. Not to hide a discovery, but to keep the university's name off a claim that might not survive the week. Bell Burnell's verdict. The claim they withheld it for too long is, in her words, wide of the mark. The lab was not sitting still. It was working down the list. Test 3. If a civilization were sending this, they would be sending it from a planet, and a planet moves. An orbiting transmitter would drift in and out of step with us as it swung around its own star. So from the 11th of December to the 5th of January, the arrival time of every pulse was tracked. There was a drift, and it was hours. Every bit of it was the Earth moving around the sun. Nothing left over. No second orbit hiding underneath. Sit with what that means for a moment. Nearly 4 weeks of watching a clock tick, on paper, to prove that nobody is standing behind it. 3 tests, 3 answers, and the alien hypothesis was still not dead. It was only cornered. What killed it was not an argument at all. While that tracking was still running, just before Christmas, in an unheated observatory, she found a second one. It is worth standing in that room. The cold has got into the electronics, and the receiver is losing gain, which means the signal is fading out of reach exactly when she needs it. The source will cross for about 5 minutes, miss it, and there is no second attempt tonight. So she flicks, switches, swears at it, breathes on the frozen components to warm them, and keeps the machine alive long enough for the paper to catch it. The second one came in at 1.2 seconds, a different patch of sky entirely, out near Cassiopeia. And that is what finished it. 2 separate civilizations, in different parts of your sky, would have to have picked the same improbable frequency and the same moment to signal the same planet. She left the recording on her supervisor's desk and went home for Christmas. By her own account, much happier. That reaction is worth sitting with. The most spectacular headline in the history of the subject had just evaporated, and the person who evaporated it felt relief. Because for her, the aliens had never been a dream. They were a threat to a thesis. She has described going home cross in those earlier weeks, because a silly lot of little green men had chosen her aerial and her frequency. So by the middle of January, there were 4 of them, one ticking a shade faster than the first, another in a different part of the sky running 5 times faster still, each keeping its own time. Whatever this object was, it was not one accident. Which leaves the question the tests could not answer. What keeps time that precisely and survives doing it? Here is the part that almost never survives the retelling. The discovery paper did not say rotating neutron star. A compact star ringing, pulsating in and out like a struck bell. White dwarf or neutron star, the paper left the choice open. A reporter at the Daily Telegraph shortened their own phrase, pulsating radio source, into one word, pulsar. The first challenge came from outside the group. At the Cambridge seminar announcing the result, Fred Hoyle stood up as soon as the presentation finished. He had heard the data for the first time that hour. He proposed the remains of a supernova instead. The shape of the answer came from Thomas Gold. Not a star ringing, but a star turning, its beams sweeping past us. The idea was ridiculed so widely that he was refused permission to present it at the first international conference on pulsars. It was settled only when the Crab pulsar turned up, 30 rotations a second, far too fast for anything ringing or pulsating. A turning body can do it. That failure is an ordinary one. Being closest to a result is not at all the same as seeing what it means. So the object had been named after a mistake, explained by outsiders to the group, and confirmed by a star that had been in plain sight the whole time. So what had they found? Take the core of a star many times heavier than the sun and remove everything holding it up. What is left is about 1.4 times the mass of the sun, packed into a sphere a couple of dozen kilometers across. A city with a star inside it. The density figure that circulates for this is usually wrong, and the wrong version is everywhere. 900 billion tons, the weight of a mountain range. Neither of those is what the measurement says. The real number is smaller, and stranger for being smaller. A teaspoon of neutron star matter, packed as tight as an atomic nucleus, weighs around 1.3 billion tons. Now put a magnetic field on it and set it spinning. The magnetic axis does not line up with the spin axis, and it never has to. So the star turns, and 2 narrow beams sweep round with it, each tracing its own circle across the sky. Nothing about the star is blinking. Nothing is switching on and off. The flashing is yours. You are the thing passing in and out of a beam that was never aimed at anyone. Which means the regularity that looked engineered is just geometry. What you are hearing is a rotation rate, written in light. And it goes further than anyone expected. The fastest one we know of turns 716 times a second. Its surface is moving at roughly a quarter of the speed of light. Not close to light speed, as the internet usually has it. A quarter is strange enough. There is one more thing about the beams, and it is the part that is still open. You can predict when a pulse arrives to an accuracy that rivals atomic clocks. And we still do not have a settled account of how that light is made, even now. Nearly 60 years on, the most familiar object in radio astronomy is still one whose light we cannot fully explain. And that is not the strangest thing it turned out to be good for. Which brings you back to the paper, because there is something else that can be done with a signal arriving on a beat. You can listen to it. Carefully worded, though, because space is a vacuum, and nothing about this is sound. What a radio telescope collects is a varying intensity over time. Feed that variation straight into a loudspeaker, and the cone moves in proportion to the incoming energy. The rhythm you hear is the literal rotation of the star. Slow ones tick. One turns like a locomotive. Another clicks like a machine gun. And then comes the crab, turning 30 times a second. And something happens that has nothing to do with astronomy. Above about 20 hertz, your ear stops hearing separate clicks and starts hearing a pitch. The ticking becomes a tone. The discovery paper appeared in February 1968. And then the press arrived, and the record of this discovery started to go wrong in a second way. Search for a photograph of this discovery, and you will almost certainly find one of two images. Both are staged. The famous portrait, with the pulsar trace behind her, was taken in 1977 by Robin Skagel. 10 years after the fact, by a professional photographer as an illustration. The field photographs, the ones with the wooden posts and the mud, were staged for reporters in early 1968, after the paper was already published. We do not have to guess at this. She described those sessions herself, 9 years later, photographed standing on a bank, sitting on a bank, examining what she called bogus records. One of them had her running down the slope, waving her arms, while a photographer shouted at her to look happy, because she had just made a discovery. The questions from the journalists were about her hair, her measurements, and how many boyfriends she had. She has said she could not push back very hard, with 6 months left on her thesis. The real scene is the one nobody photographed. You are up in that attic, bent over the chart, a coordinate written by hand in the margin. There is a third image you will meet, and it is one of the most reproduced graphics in astronomy. Stacked white ridgelines on a black cover. It is not raw data, and it is not a Fourier analysis, whatever the caption says. It is a plot of 80 successive pulses, stacked, drawn by Harold Kraft for his doctoral thesis in 1970. That plot became an album cover, and it is still the picture people mean when they say pulsar. And then there is the prize. The 1974 Nobel Prize in Physics went to Hewish, her supervisor, and to the head of the group. She was not named. Her own position on it is not the one people expect. She has argued that supervisors carry final responsibility for a project and should share in its successes, and that she has done rather well out of not getting it. Whether that settles it is not really ours to decide here. The argument has outlasted the prize. The signal does not care. What it turned into is easier to measure than what it meant. Pulsars turned out to be clocks. Not perfect ones, and not the replacement for atomic time that was once expected, but steady enough to check it against. Stable enough that arrays of them are now watched together, listening for a gravitational wave stretching and squeezing space itself as it passes through the galaxy. Stable enough that NASA's nicer instrument can work out where a spacecraft is by timing X-ray pulses, the way ships once found their way by lighthouses, a known rhythm in a known place. And on the cover of the Voyager record, bolted to a spacecraft now in interstellar space, there is a diagram. Lines radiating from a point, each one labeled with a rhythm. It is a map of pulsars. It says, "This is where we were, and this is when." Our address is written in the timing of dead stars. That rhythm was only ink. Nearly 60 years ago, 5 millimeters of it, easy to throw away. It was not thrown away, because one person went back and checked whether it had been there before. That is the whole mechanism, not the telescope and not the argument that followed it. The beam is still sweeping. It crossed this planet about 1,000 times while you were watching, and it will keep crossing it whether or not anyone is left to draw the line. There is a mirror image of this story, a signal we built ourselves and then sat listening to as it went quiet. That full journey continues on the channel.